All right, we're going to talk about a couple of things today. The first thing we're going to talk about is rotational inertia. After taking the rotational inertia notes, you should go and check out the video I have linked below this one. And it's a demonstration from Flipping Physics on rotational inertia. So basically, rotational inertia is the linear analog to mass. So for linear quantities, we use mass measured in kilograms. Well, for angular, we have to look at inertia or rotational inertia or moment of inertia. We represent that with an I, and its units are kilograms meters squared because it is related to not only the mass of the object, but its radius. Now, you're only talking about angular or rotational inertia when you're either getting ready to rotate something or something that is already rotating. For a point mass, we have an equation for rotational inertia. So a point mass is basically any object with uniform mass. So a meter stick would be a good example of a point, something we could make into a point mass. So the equation for that is rotational inertia is equal to the mass times the radius squared. So R is radius and M is mass. Okay, so again, I mentioned this before, that rotational inertia is dependent upon an object's, not only its mass, but its radius also. If we're talking about a distributed mass, so we're talking about something that has mass that varies, then we are talking about something like a hammer that has a heavier end to it. Then we have to use calculus, and we will be going more into the calculus next week because calculus AB and BC, you guys are finally to integrals, so we can add that into our toolbox. Something that is a distributed mass, again, it's like a hammer, a hockey stick, a baseball bat, anything that has a heavier end to it. It's not a uniform distributed mass. We have to use integral calculus, and basically you can find the rotational inertia by taking the integral of the radius squared with respect to mass. We will talk a little bit more about this in a separate video. I will show you how to derive the rotational inertias using calculus. But for now, you can use the table that I gave you last class with all of the rotational inertias on it. So this is the table I gave you last time. Something I'm not sure if I added on the previous video or not. A disc is considered a solid cylinder, or similar to a solid cylinder, because a disc is just as if I took a slice of a cylinder, so its rotational inertia is the same. So same thing over here. This will also apply to a disc. So you can rotate things about their central axis, that is the axis going through the middle here, but we could also rotate them on a axis vertically and then rotate it that way. Okay, so all of these rotational inertias are for these orientations through their centers. And remember, we talked last time, like in the case of this one, the rotational inertia, or where that object will rotate around, does not need to be part of the physical object. All right. Well, we can move the axis of rotation. So let's say if we're looking at this one right here, let's say we're not going to rotate it around the center. We're going to move it over here and rotate it around one of the ends. Well, now this is no longer the rotational inertia for that object. We have to use something called the parallel axis theorem. So I believe this was covered in the Walter Lewin video last time, but I'm going to just kind of summarize it here as well. So the parallel axis theorem deals with when we move that axis of rotation. And the parallel axis theorem says that the new rotational inertia is going to be equal to that rotational inertia around its center, which is where things will naturally rotate around. That relates to their center of mass as well, by the way. Plus the mass of that object times the distance you moved it from the center. Okay, so This is the inertia around the center. Rotating it around the center. So again, it's the center of the object or system. M is mass. And then the D is the distance you moved it from the center. You have some practice problems today with rotational inertia and the parallel axis theorem. I will have a video where I do a couple of examples of those and some additional practice over that. There will be a question on the AP test that goes over parallel axis theorem. It will either be a multiple choice question or it will be embedded in a free response question. Okay, we've already talked about a lot of the relationships between angular and linear quantities. And we filled in this table for everything up at the top. So we're going to fill in some more here at the bottom. All right, so force we're going to talk about next time. But kinetic energy, we're going to go ahead and fill that one in right now. So linear kinetic energy is 1/2 the mass times the velocity squared. Well, rotational kinetic energy, and sometimes you'll see a T down here for translational. Sometimes they'll write rotational in here. It's 1/2. Well, instead of mass, we use rotational inertia. And instead of linear velocity, we use angular velocity. So rotational kinetic energy is just the rotational inertia times the angular speed or velocity squared. All right, work, spring force, we'll talk about those next time. Spring potential energy, we're not going to worry about that right now. You're going to be talking about angular momentum today. So linear momentum is just mass times velocity. Angular momentum is represented with an L. And again, you just swap out the rotational inertia for the mass and angular velocity for the velocity here, okay? You may see another equation for angular velocity, so let's go ahead and derive that right now. So linear momentum, sorry, not for angular velocity, for angular momentum. Linear momentum is mass times velocity. Angular momentum is the rotational inertia times the angular velocity. I'm going to use rotational inertia for a point mass and substitute mr squared in for the rotational inertia. And then angular velocity can be found by taking linear velocity divided by radius. So I'm going to substitute those into my angular momentum equation. So I get mr squared times velocity divided by radius. One of these goes away. So you can see I have a new equation for angular momentum. You can compare that to the linear momentum. So this is a little bit different than what we did before when we bridged between the two. So let me go back to the table. So previously, to get from linear velocity to an angular velocity, you would multiply the angular velocity by the radius, or to get to the angular velocity, you would divide the linear velocity by the radius. Well, we also have a bridge here that the angular momentum is mass times velocity times the radius, or linear momentum times the radius. Okay, so this is a little bit different than up at the top when we did the angular multiplied by the radius. Now we do the linear multiplied by the radius, and that's because of that r squared embedded in the rotational inertia. The conservation of momentum, initial momentum had to equal the final momentum in all directions, x and y. Well, we get the same thing in angular momentum, except for now it's the initial angular momentum has to equal the final, which means in all directions, clockwise and counterclockwise. So we have two directions that we talk about with rotational motion. Something's either moving clockwise or CW. That is a negative direction, or it's moving counterclockwise, which you'll see as CCW. Oops, I can't do that. and that one is positive. That's due to the right-hand rule, okay? So clockwise, the normal direction around a clock, counterclockwise, the opposite direction. So I will post a video on the right-hand rule. I'm sure it's covered in the Walter Lewin video as well. I'm unable to demonstrate that here with this technology, so you'll have to look at one of the other example videos, okay? So that's all we're working on for today. You're going to have some kinetic energy rotational problems. You had one last time as well. And you're going to be doing momentum, conservation of momentum, and then the inertia and rotational inertia notes I covered a minute ago, okay? So let's talk about a few different types of examples you may see. So we have objects rolling down a ramp. And we're going to look at the kinetic energy of that and what happens when you add rolling in. So now rolling down a ramp means that I still have a conservation of energy equation. So whatever my initial kinetic energy is plus my initial gravitational potential energy has to equal my final kinetic energy plus my final gravitational potential energy. So this is if you had something that's not rolling, okay? So sliding. And the difference between that is that you have something that is just sliding down under the influence of gravity. Something that's rolling actually has a frictional force on it, and we'll go into that more next time. But you have to have friction in order to roll. So just keep that in mind, even though they will say frictionless and something's rolling down it. It's just to simplify the problem. Okay, so here's my object rolling down the ramp, and we want to know the final velocity at the bottom. Well, if it starts from rest at the top, then we get our gravitational potential energy at the beginning is equal to now not only our translational kinetic energy, but our rotational kinetic energy, as well, okay? So that means I would have mgh equals 1/2 mv squared plus 1/2 the iw squared, or the rotational inertia times the angular velocity. Now, when you do these, you're going to want to either make everything linear or make everything angular. So usually we make everything linear because we have meters over here. So on the right hand side, we would convert this to a linear quantity by taking the rotational inertia of whatever the object is around its center, and then using velocity divided by radius for the angular velocity, okay? So that's a typical rolling down the ramp problem. Usually momentum doesn't come into play there. We will get momentum, though, when we do something striking a thin rod. So you're going to have a lab today that is going to explore what happens in collisions when something is caused to rotate. Okay, so we have this little bar here that's hanging. It has a mass. Of course, it has a length. Let me rewrite that somewhere else. Okay, so it has a mass, and then it has a length. So if we're talking about a bar, we're talking about length, and we're talking about surface area. I'll go into more of that in the video on deriving the rotational inertias. All right, I'm going to have a mass over here, a smaller one. It's going to come in and hit this. Let me do M1 and M2 so it's easier to see. Okay, so this is your initial. All right, then we have the moment of the collision. When the sphere just taps it, it's going to cause this to rotate. And we're looking for its angular velocity. Okay, so again, it's a conservation of angular momentum. So we had a linear velocity to start with. That's why I have it written in linear quantities. Then we have angular quantities to contend with on the other side. We have a parallel axis theorem problem here because rotation, let me do a different color. Normal rotation would happen here. That's what we would call the rotational inertia about its center. But we move the axis of rotation up to the top. So you would have to use parallel axis theorem for the rotational inertia, not just the given rotational inertia in the table. So again, this right here comes from the table. I just realized I did not give you the rotational inertia of a bar in the table. So this would be given to you in the problem, or you might have to look it up, okay? So this is M1. This is M2. You get the 1/3 here because we moved it from the center, okay? And again, as you do the problems, as you do some rotational problems, this will start to make sense, okay? Merry-go-round is another example, or a carousel. So we have a disc here with a radius r and a mass m1. And we have a person standing on the merry-go-round, and they are going to throw a stone from the merry-go-round, okay? And the stone is going to have some sort of velocity. Well, the initial angular velocity is 0, so it's at rest. So after the person throws the stone, what is the angular velocity going to be? Well, this is still a conservation of angular momentum problem. In this example, the angular momentum is equal to 0 initially. So we have a conservation of energy. Here's your situation that's going on. That means the angular momentum of the merry-go-round plus the person has to equal the angular momentum of the stone. Okay, so we end up with the I times the final angular velocity there is going to equal that radius of the merry-go-round times the momentum of the stone. Okay, so what you end up with is, 1/2 mr squared, because that is the rotational inertia and for the merry-go-round, plus the mass of the person times its the person's radius squared times its final angular velocity, and that's going to equal the radius of this merry-go-round times the mass of the stone times the velocity of the stone. Now this will make more sense as we go through and do the practice problems, okay? Again, the biggest mistakes I see students make are mixing angular and linear quantities together instead of converting either all to angular or all to linear, okay? So try the practice. The answer key will be posted later this afternoon. If you have questions, let me know. I will probably also I'm going to do the video with deriving the rotational inertias, and then I will do a video probably with a couple of example problems to walk you through those, okay? So if you have questions, let me know. Otherwise, have a great day.